Okay, in this video, we want to show that if we have a sequence of real numbers and that sequence is Cauchy, then it converges. And again, the idea is that if we want to show a sequence converges, up until this point, we've had to have a guess for what the limit is. Now, just by looking at the sequence without trying to guess what the limit is, if we just know the terms of the sequence are getting closer and closer to each other, we know that it converges if it's a sequence of real numbers. And so that's what we're going to prove here. So we're going to prove the following fact. Let me get a good color. If we have a Cauchy sequence, so if AK is Cauchy, and again, it's a sequence of real numbers, then it converges. Okay, so I'm going to prove this, but let's first think through what's going on here. So first, let me show you what I'm going to prove. What I'm going to prove is that the lim inf is equal to the lim sup. Because in a few videos ago or a few theorems ago, we proved that whenever we have a sequence and the lim inf is equal to the lim sup, then the sequence converges to whatever that number is. So that if the lim inf is 5 and the lim sup is 5, the sequence converges to 5. So that's what we're going to prove. Ultimately, the goal is to prove that the lim inf is equal to the lim sup. Now, to know, we always know the lim inf and the lim sup are going to converge. It might converge to plus or minus infinity, but how do we know they converge to real numbers? Well, number one, the sequence in the definition of lim inf and lim sup, so the sequence in the definition of lim inf is increasing. The sequence in the definition of lim sup is decreasing. And since the AK sequence is Cauchy, we know it's bounded. Okay, so the sequence, the UK sequence in the definition of lim inf is an increasing bounded sequence, and the VK sequence in the definition of lim sup is a decreasing bounded sequence. So this means they both exist. The lim inf and the lim sup both exist, and they're real numbers. Okay, now we always know that the lim inf is less than or equal to the lim sup, because the UKs are lower bounds and the VKs are upper bounds, and lower bounds are always smaller than upper bounds, less than or equal to upper bounds. So this means that the lim inf, which we call U, is less than or equal to the lim sup, which we call V. So we know U is less than or equal to V, and we want to prove U is equal to V. And you might remember from 300 one way to do that. If I want to prove U is equal to V, one way is to prove that U is less than or equal to V, and V is less than or equal to U. Therefore, U and V are equal to each other. So we already know that U is less than or equal to V. What we want to prove is that V is less than or equal to U. And actually, we're not going to prove V is less than or equal to U directly. We're going to prove that V is less than or equal to U plus epsilon for any epsilon greater than 0. Okay, so that's the idea. We want to prove that the lim sup is less than or equal to the lim inf plus epsilon for any epsilon greater than 0. So let's just think through why this might be true. Okay, so the idea, and so now what I want you to do, I want you to go back and look at the video. We've proven something similar before. I want to prove the lim inf is equal to the lim sup. We've done that before. We've shown that if a sequence converges, the lim inf is equal to the lim sup. Our hypothesis is different in this video. In this video, we don't know that the limit exists. We know the sequence is Cauchy, but we're proving the same thing. Go back and watch that video and see if you can make a proof of this theorem, because it's going to be very, very similar. Okay, the ideas are going to be very similar. So if I have a sequence AK, and I know that the tail end of the sequence, the terms are very, very close to each other, this means that the lim inf and the lim sup are getting closer to each other. The lim inf is a lower bound, but it's the least lower bound. So as the AKs go up, it's going to sort of pull the AKs up. As the AKs go down, it's going to sort of pull the lim sup down. Okay, if I know that I can make the tail end of the sequence, if I know that I can make the AKs and the tail end of the sequence very close to each other, that means the least upper bound and the greatest lower bound have to be close to each other as well, which means that the lim inf sequence is converging to the lim sup sequence, and so they're going to be equal, and so the sequence itself will converge. Now, I hope you pause the video and try to figure out a proof for this using the hint that I gave you. But remember, in that video, in the video, in the proof where we show that if a sequence converges, the lim inf is equal to the lim sup, one of the things that we did is we showed that L plus epsilon is an upper bound and L minus epsilon was a lower bound for the tail end of the sequence. So let me come back over here and write, we will show that V is less than or equal to U plus epsilon. Here, V is the lim sup and U is the lim inf for all epsilon greater than 0. Okay, and the explanation that I give before will explain why this means the sequence converges, because this means V is equal to U. Okay, you will show that V is less than or equal to U plus epsilon for all epsilon greater than 0. This implies that V is less than or equal to U. We already know U is less than or equal to V, so this means the lim inf is equal to the lim sup, which means the sequence converges to whatever that value is by a theorem that we looked at a few videos ago. Okay, so how are we going to do this? So let epsilon be greater than 0, choose, and it might, I don't know if it's going to end up being epsilon, it might be like 4 epsilon there or something, so I might have to come back and change that. Choose in such that for all k and L greater than n, AK minus AL is less than epsilon. So if in particular I take L is equal to n plus 1, then, and think about why this inequality is true if you don't get it, then A n plus 1 minus epsilon is less than AK is less than A n plus 1 plus epsilon. Okay, so now what this means, it means that an plus 1 is a lower bound and an plus 1 minus epsilon it means an plus 1 plus epsilon and an plus 1 minus epsilon is a lower bound for the tail end of the sequence. So an plus 1 is a lower bound, and an plus 1 minus epsilon and an plus 1 plus epsilon is an upper bound for the set AL where L is greater than n. Okay. Okay, so therefore, so what do we know? So I know by definition the greatest lower bound of this set is un. An plus 1 minus epsilon is a lower bound. So what this means is an plus 1 minus epsilon is less than un. So I know an plus 1 minus epsilon is less than un. Okay, and I know that un, I know that Vn is the least upper bound for this set. An plus 1 plus epsilon is an upper bound for this set. Vn is the least upper bound, so I know this Vn plus 1 has to be less than an plus 1 plus epsilon. Okay, so now I'm going to have this string of inequalities. Well, so let me mention a few other things. Since this pin thing is really irritating me. Since Vk is a decreasing sequence, this means that Vk is greater than or equal to V because it's coming down. It's coming down to the limit. And since UK, oh, come on now. UK is increasing Since UK is increasing, I know that UK is less than or equal to UK is less than or equal to the lim inf u. Okay, so now I'll have a string of inequalities. I want to show v is less than or equal to u plus epsilon. So the left-hand side of my string of inequalities is going to be v. I know that v, because of this inequality, is less than or equal to vn. Because of this inequality, I know vn is less than an plus 1 plus epsilon. So this is less than, sorry, these are actually less than or equal to, aren't they? This is less than or equal to an plus 1 plus epsilon. Okay, if I look at this inequality, if I look at that inequality, that tells me an plus 1 is less than un plus epsilon. Or if I just add 2 epsilon to this inequality, it tells me an plus 1 plus epsilon is less than or equal to un plus epsilon, plus 2 epsilon, plus epsilon. So this plus 2 epsilon, sorry, let me explain that one more time. If I add 2 epsilon to this inequality, the left-hand side is an plus 1, and the right-hand side is un plus 2 epsilon. So this is going to be less than or equal to un plus 2 epsilon. And I know that un is less than or equal to u. So this is less than or equal to u plus 2 epsilon. Okay, so I've proven that v is less than or equal to 2 plus epsilon, which is exactly what I said I wanted to prove. Modulo this little thing here, it needed to be a 2 instead of an epsilon. At any rate, we know, or I want you to think about this, we've explained it in class, that if I know that v is less than or equal to u plus 2 epsilon for all epsilon greater than 0, then v is less than or equal to u. Okay, so this is a proof of a very important fact. I want you to do the following. After you understand the proof, or maybe even before you understand the proof, this is not true. If we just deal with rational numbers, this theorem is not true. There are Cauchy sequences of rational numbers that don't converge to a rational number. The reason that it's true for real numbers is that the real numbers have this property called completeness, and that lets this proof work. So I want you guys to think through which part of this proof is not going to work if I'm only looking in the world of rational numbers. There's no point explicitly where we said by the completeness axiom such and such a thing is true, so you'll probably have to think about it for a little bit, but it's worthwhile.